Now we're ready to take up chapter 6. Chapter 6 begins with a consideration of light. This is a little bit of a strange topic to be bringing up in a chemistry course. Chemistry is most often defined as being the science of matter, and matter is usually defined as being anything that has mass, which would put light somewhat out of the boundaries of chemistry. The reason we're going to talk about light is because light turns out to be a very powerful tool for helping us to learn things about atoms. A lot of what we know about atoms and molecules is the result of experiments that involve interactions between light and those small particles, right? And we'll see as we go along why that is and why light is so appropriate as a probe for things involving the energies of atoms and molecules. What we're going to talk about in this first video is mainly the so-called wave-particle duality, the idea that light can be thought of as a wave or as a particle, and that both of those descriptions can be useful. We use them both in different circumstances and for different reasons, okay? Some level, what this really means is that neither the wave model nor the particle model is an entirely good description of light, because if it were, it seems like it should be able to describe all of the things that we can observe about light, and we wouldn't have to toggle between two different models. But at least for now, that's what we do. We come to familiarize ourselves with what are the circumstances we need to think about light in terms of this particle idea, and when can I revert back to a more traditional or classical physics kind of notion of light as being like a wave. I'm going to start off on the wave side of things because, at least partly because that's historically how light was thought of and described. Okay, so when we talk about light as a wave, we need to just get a little bit of a refresher about some wave properties and the parameters that describe waves. Okay. In this slide, my wave is just a simple sine wave, okay? So imagine that that wave is traveling, say, from left to right across the screen. I have marked on here, first we'll look at a wavelength. That symbol there, that is the Greek letter lambda, okay? And that is the symbol that is generally used for wavelength. The wavelength, it says length in its name, right? That's going to have distance units, and typically we will most often express our wavelengths in nanometers, okay? Remember, 1 nanometer is equal to 10 to the minus 9 meters. If you don't already know that prefix, you will by the time you get through doing some problems in this portion of the course, okay? And so that's a length unit. It describes the repeat distance of the wave. So if I mark here and here, for example, those are both points where the wave is going through the through zero on the vertical scale, and where it is rising. Okay, so those are two identical or indistinguishable points. I could also have marked, say, the tops of the crests here, right? If I went from there to there, that would be a wavelength. Or I could have gone from valley to valley. All of those things, if I'm dealing with an ordinary sine wave, they should all be the same distance, okay? If I had a wave that was more complicated, by the way, that could not be described as a single sine wave like this, we'd be able to take it apart and make it a sum of several different waves, all of which we could break down into individual things like this. So we can always get away with that part, even for a more complicated looking wave. Waves also have amplitude. So this A over here represents the amplitude. That amplitude is in this case just going to be the height, the maximum height of the wave, right? It's usually measured as drawn there, where it's the half of the peak to peak height. That's because if I wrote an equation for this wave, I'd take my sine function, I would just multiply it by A out in front, right? Because the sine function itself would go from -1 to +1 for its extrema, and then multiplying by A would just scale it up for the actual amplitude of the wave. I find it useful to correlate these properties with what's actually perceivable about the wave. So if my wave is light, the amplitude would be a description of how bright is the light. The wavelength would correlate with what color is the light, okay? Those are two ways to think about those specific properties. At least for me, thinking of it in that way helps me avoid some possible confusions that I do see people stumble into from time to time. The other parameter that we'll see most often for waves is the frequency. Frequency has this symbol here. That is a Greek letter nu, Nu. and that little squiggly V sign there. Frequency and wavelength are inversely related to one another, okay? Because the speed of light is constant, the frequency and the wavelength are not independent of each other. They are both ways of specifying what color the light would be in that instance, okay? Imagine if I was just a stationary observer. So suppose I was looking at a point here as these waves traveled from left to right across the screen, okay? What I could do to get a measure of the frequency is I could count how many peaks, how many maxima go by that point per unit time, right? So if I watch for a second, I could count up how many of those individual cycles of the wave go past, okay? Frequency, therefore, is going to be measured in units of often written just as 1/time. So in 1/seconds, that also gets a name that is referred to as Hertz, abbreviated HZ. That stands for Hertz, which is the name of a person involved in the historical development of some of these things, okay? As this particular figure shows us, the frequency within visible light, the frequency is low for red light and it is high for blue and violet lights, okay? And it varies across there. You'll notice the arrows here going in different directions, right? The frequency increases when the wavelength decreases. And again, I can't change those two things independently of one another. They're locked in place because the speed of light is a fixed quantity. And in just a second, I think we'll meet up with an equation that would help us out to do that. Some orders of magnitude for things. The wavelengths of visible light are typically between about 400 and 700 nanometers, okay? On this red up here, this would be wavelengths of somewhere around 700 nanometers. Down here on the purpley end, that would be somewhere around 400 nanometers. Those are more or less the limits of what an average human eye can detect, okay? If we go beyond those things, we go into the infrared or the ultraviolet, where your eye is no longer sensitive. You don't see those as colors, although there are still waves, there's still radiation there. We'll talk about that some too towards the end of this video. Another property of waves is, this is a peculiar thing about waves, it very strongly distinguishes waves from particles. Waves can interfere with one another, okay? And they can interfere in two different ways depending on what is known as the phase of the wave. So in these two figures, the two waves on the bottom are a pair of sine waves. They're a pair of sine waves that have the same wavelength / frequency as one another, right? On the left-hand panel, they are in an arrangement that is referred to as in phase. What does that mean? It means that they're both hitting maxima at the same time. They're both hitting minima at the same time, and so on. They're both crossing zeros at the same time, right? So if I took those two waves and added them together, what I get is a wave that still has the same wavelength and frequency, but it's twice as big. I would just double the amplitude because I could add those two waves by just doing a point-by-point sum of the two values, right? That's just going to make a wave that's twice as large, okay? On the right-hand side, I have the situation where the waves are totally out of phase. So now, where one of them is at a maximum, the other one is at a minimum, okay? Maximum and minimum come together. So on that instance, if I were to take those two waves and add them up, what's going to happen? They're going to mutually annihilate. They're going to undergo destructive interference, and the result is going to be that there'll be no wave at all left, okay? Particles don't do this. You can't take two small particles and throw them up against each other and have them turn into a bigger one, right? Similarly, you can't take two baseballs and throw them together and have them just wipe one another out and disappear, right? They're not capable of this interference phenomenon. This is a thing that waves can do and particles cannot, okay? Light very definitely does this. There are experiments, gosh, lots of things that are what's known as diffraction. In live class, I will probably show some sort of video that shows a little bit of diffraction. If we were meeting in the classroom, I usually bring a diffraction grating and some light sources and look at how different colors of light would diffract through a so-called diffraction grating slide and look at that. But that's a wave property, and light very definitely does it, okay? And that tells us that it is valid to think about light as being a wave under lots of different circumstances. In fact, if you went back to the early the 19th century, let's say, and asked a physicist, what do you know about light? They would have told you they had it all figured out, would have described it entirely in terms of waves, and that would have explained all the things, all the observations they had available to them. So it was a reasonable inference on their part to say that, like, yeah, that made sense. So here is the promised equation relating the speed of light, wavelength, and frequency. Okay, c is the speed of light. So this is the speed of light. It is a fixed constant. Lambda is wavelength, and nu is frequency. Okay. The speed of light, for practical purposes, we will usually get away fine with using just 3 times 10 to the 8th meters per second. Okay. For our purposes, if you look at that number 3 times 10 to the 8th meters per second, that's good to at least 3 significant digits from what the actual number is there, and we only rarely do problems that have more digits and everything than that. This is actually an exact number, so if you want the official speed of light, it is that with all of those digits and with no subsequent digits, because the speed of light is now a defined quantity, meaning that the meter and the second are defined in terms of that being the speed of light, rather than the other way around nowadays. That's mostly for people that are into sort of the gory details of measurement stuff. If we think about this equation in terms of units, it should make sense. We can make sure it works, right? The speed of light, c is the speed of light, so it's got to be in meters per second, right? Lambda is wavelength. That's going to be in distance units. I'm going to put it in meters for right now. Nu is a frequency. I mentioned that that could be written as 1/seconds, right? So my units work. That tells me my equation works out. This is an equation that, again, has 3 things in it, and one of them is a constant, c. So there's really just 2 things there, lambda and nu. That means if I know either lambda or nu, I automatically know the other one, okay? Because I always know c, the speed, right? The speed of light is a universal constant. It is not a variable, okay? Either lambda or nu, those are 2 ways of specifying what color you would see the light as, all right? Note that knowing the color of the light is not related to how bright it is. If I say it that way, you won't doubt that for an instant, right? But it's important to keep in mind that knowing the color of the light, knowing the frequency or the wavelength of the light is also not related to how bright or how intense the light is. That's a point that I can get you confused about if I say things in certain ways and if you're not thinking about things carefully. Okay, it's not my goal to get you confused, which is why I'm trying hard to make the point that it's useful to think about things in terms of like, well, that's about color, and this is about how bright it is. And that will make clear to you that those should be separable things. There shouldn't be a linkage between what color the light is and how bright it is, right? If I had a blue light bulb or a source, I could turn the brightness up or down and it wouldn't change the color. Sometime in the early 20th century, there's a lot of experiments going on because of some technological advances that make the experiments possible, and they lead to a number of discoveries that sort of break that wave model of light. Okay, when I say break it, I mean there are some observations that the wave picture simply can't explain well. Right? We'll talk about one of these experiments, at least in some detail, in the subsequent video after this. The photoelectric effect is one that I like to talk about a bit. Right? In order to explain these observations, what happens is that a group of scientists at the time, including Max Planck, Einstein, and others, settle on this notion that light can be described as a collection of what the word they choose for these are photons, where a photon is, in loose terminology, a, quote, particle of light. So when we say this is a particle model, photon is the name we give one of those particles. What does this mean? It means the energy that's contained in a light, in the radiation emitted from a light, can be thought of as broken down into discrete little chunks, and that there has to be some whole number of those, okay? Those photons have an energy where the energy depends on the frequency. This is often referred to as the Planck equation. It says the energy of a photon is equal to h times nu. H is a constant known as Planck's constant. It has this value here, okay, in SI units. Nu is the frequency. I could also write this if I wanted to in terms of wavelength, because I have what C is equal to lambda nu. That means nu is equal to C over lambda. So that says I could make this HC over lambda if I wanted to express it in terms of wavelength, all right? It's reasonable right now if you're thinking like, I don't think light is like that, right? I don't, when I look at any sort of light source, even if it's pretty dim, I don't stare at it and say like, oh, there goes a little bit of light now, and here's some more, and here's some more, right? I have no perception of these individual photons or increments of light. The reason for that is this piece of this number right here, the 10 to the minus 34th joule seconds, okay? As we'll see in a moment, that makes the energy of any one of these photons be very, very small, too small to be perceptible by something the size of a human, okay, or even a human eye. But if you were the size of an atom or a molecule, the energy of one of those photons would actually be substantial to you. It would be enough to do serious disruption of your world, okay? And so that's why light turns out to be a good tool for exploring atoms and molecules, is because the energies of these photons are of similar orders of magnitude to the kinds of energies associated with small particles like atoms and molecules, okay? And that's why we're talking about light right now in our chemistry course. Let's take up a little bit of an exploratory example of what exactly the energy of a photon might be. So I'm going to do a quick calculation here. Laser emits red light with a wavelength of about 633 nanometers. This is generally what would be just an ordinary red laser pointer, right? This has always been in my slides, and if I were in physical classroom, I'd be sort of waving the laser pointer around right now saying, this is the light I'm talking about, okay? That 633 nanometers is definitely a red color to the human eye, okay? First, I'm going to calculate what is the energy of a photon at that wavelength. We just saw an equation that will let me do that. Then the second part of the question, which is one that some of you might find a little bit more challenging or less obvious how to do, is we're going to take and say that my laser has an output power of 1 milliwatt, or 10 to the minus 3 joules per second. And I'm going to use that fact to calculate how many photons are emitted by this laser per second. So if you want, you might pause the video and take a moment to think about how you might do at least that second part of the calculation. The first part, I hope, is relatively obvious. So the first thing I'm going to do is I'm going to find my photon energy, right? We just met an equation a couple of slides ago that says the energy of a photon, I'm going to write the photon piece on here for emphasis right now, is equal to h times nu. And another way to write that is hc times lambda. All right. H is a constant, C is a constant. Those are just numbers. So all I have to do is basically put them in there together with lambda. You probably don't know the value of H just yet off the top of your head, but you will once you do some problems in this chapter. And this is 6.626 times 10 to the minus 34th power. That's in units of joules and seconds. C, the speed of light. I said before we could get away for pretty much all of our purposes with 3 times 10 to the 8th meters per second. So let me put that in. Meters, I did not write that. And then I want to put lambda on the bottom. I'm going to do something a little bit peculiar looking here for my lambda. I'm going to put 633 first. Then I'm going to remember this is in nanometers, okay? My distance unit on top, if I look at the top right now, the seconds will cancel. Right? So right now, the top of my expression is in joules times meters. I want an energy, so I want to end up in joules, right? That means I want to cancel the meters. So I'm going to take my 633 nanometers and I'm going to write it as 633 times 10 to the minus 9 meters. If I don't do that, I can fix it afterwards as long as I'm paying attention, right? Because then if I put nanometers there, if I just put 633, I'd say now I have joules times meters over nanometers, and I'd have to get the conversion factor out to cancel my meters and nanometers. That would get me that 10 to the minus 9. Multiply that thing out, and I happen to have notes beside me that say I get 3.14 times 10 to the minus 19 joules. Okay. 2 things about that number. Number 1, that order of magnitude, 10 to the minus 19 joules. If you're calculating a photon energy for visible light, that's the magnitude you should expect to be getting. If you get a number that's around there, you probably did everything right. If, for example, I had put 633 down there and left off that times 10 to the minus 9, that would change my answer by a factor of 1 billion, right? That's enough to matter. I would notice, hopefully, that my number was not in the right general order of magnitude if I did that, okay? And then I'd get a chance to realize what I had done and fix my calculation. Number 2, look at the size of that number, 10 to the minus 19 joules. I don't know how good a sense you have of how much energy a joule is, but a joule is an energy, after all, that's associated with units, the base units, right? Kilograms and meters, right? And so a joule is an energy that's associated with things that are not that huge of a deal to a person, right? If something hits you with an energy of 1 joule, it's not going to knock you over or anything like that. 10 to the minus 19 joules, that means is an imperceivably small amount of energy, right? That's why you're not in any way aware that there are these individual photons in a beam of light that you're looking at. Okay, there is literally no way you could reasonably discern that that increment of energy had struck you or struck your retina or anything like that. Okay. This brings us to the second part of the question, which will help as well for this idea of not being able to tell that there are photons there. I have my 1 milliwatt here, right? Which again, that means that I have 10 to the minus 3 joules per second. I want to know how many photons per second. Right now, I know that each photon is equal to this number, 3 times 10 to the minus 19 joules. So another way of phrasing that, how many photons per second, is how many of these 3.14 times 10 to the minus 19 joule increments do I need to add up to 10 to the minus 3 joules? I can find that answer simply by dividing, right? And so I might do this by saying something like that I have, let's do it this way. Let's say that I have, that'll be upside down. So let's say that 1 photon, I'm trying to get to photons per second, right? So 1 photon has an energy of 3.14 times 10 to the minus 19 joules, right? 1 photons is kind of illiterate, so let's not do that. If I take that and I say, I want this amount up here, I know I need to get 10 to the minus 3 joules every 1 second. So if I divide those numbers, it's going to tell me how many of those 10 to the minus 19 joule photons I need to add up to 10 to the minus 3 joules. My units are going to come out now in photons per second, right? My number when I do that is equal to, and it might have made more sense if I started with this power and wrote it in that direction. So I'm sorry that I wrote it this way perhaps, but it's still the same number. And then I'll get 3.18, it says over here, times 10 to the 15th. That's in photons per second. All right. This is, again, a fairly run-of-the-mill laser pointer. Gosh, typically in real class, I have the laser pointer that's built into the instructor version of the iClicker device, and its power is somewhere right around there. It is not by any means an overwhelming amount of light. That says it emits 10 to the 15th photons each and every second. That's why you can't tell that those photons are actually individually incoming, right? It's sort of the same way as when a modern printer prints something, or when you look at a picture on a modern TV set, right? If you look at a 4K TV, you know there are pixels in there, right? You know there are individual dots, but you sure can't tell they're there, right? Because there's just so many of them and each one is so small. The same is true of these photons. They just have so little energy individually that our eyes can't really detect them one by one. We do have detectors that can do that. There's a way to measure light that's referred to just as photon counting, because there are devices that literally will just tell you this is how many photons hit that little sensor piece in the last unit of time that you looked at it or anything like that. So it is a measurable thing. It's just not something that your eye can easily detect. Last second here, just take a moment and look at the electromagnetic spectrum. I mentioned visible light. I want to emphasize the idea that the only thing that is special about visible light is the fact that we're humans. That's the only thing that makes us think visible light is somehow different from any of the rest of those things, right? Calling it the visible spectrum or visible light just refers to the fact that we happen to be able to see it. All of those different ranges there, from gamma rays through radio waves, they all are the same type of radiation. They're all what is referred to as electromagnetic radiation. That means they are mutually perpendicular, oscillating electric and magnetic fields, and all that kind of stuff. They all travel at the speed of light. You'll notice that the scales on here on the top, there is a frequency scale, right? And frequency is increasing from right to left on this slide, while wavelength is increasing from left to right. Those have to go in opposite directions, right? Because frequency and wavelength multiply together to make the speed of light, okay? You'll see that on the left-hand side of the screen there, we've got gamma rays. Those have up to some very large energies, right? Things 10 to the 20th hertz out there. If you were to calculate the photon energy for one of those, it's going to be a sizable amount of energy, right? And so those gamma rays, for example, are things that there's people that launch satellites for communications and other purposes have to do some things to make sure their equipment is properly shielded. Otherwise, if it gets struck by the wrong gamma ray photon, it could just obliterate all the electronics in your satellite. And so there's a lot of work done for that. Some people test a bunch of things related to that sort of thing at the cyclotron here on campus. We go through, as we go towards the longer wavelengths, we get X-rays, ultraviolet light. Then we get to the visible part of the spectrum, which has our little rainbow spectrum down there as the colors that we perceive it. Then IR and microwaves. Every last one of those pieces of the spectrum, they behave the same. They all travel at the speed of light. They all follow the same rules, okay? It's just a question of the frequencies and energies. Obviously, technologically, we use different energy ranges there for different purposes, and a lot of that is based on the photon energies and what they interact with.